Oh,
Uh,
Graham.
what is going on? You guys are making me feel a little disoriented. What is going on there?
Oh, well, we said we were going to talk about the motions of the atmosphere and oceans today. So we're working on that.
Yeah, you're making me a little dizzy.
We're kind of lost at sea out here, Marisa. I just got my sea legs and a storm rolled in.
Oh. Yeah, there it seems like there's quite a lot of motions for us to be talking about today by the looks of you two.
You
Oof.
better believe it. Well, may as well hop right into it, huh?
Great. Yeah, so for today's Rockin Pop-Up, our November Rockin Pop-Up, we are talking about the motions of the oceans and the atmosphere. Take it away, guys.
Thanks, Marisa. So yeah, Gavin and I are really wishing we decided to hop on those hot air balloons instead, but we'll do the best we can from out here at sea. So, Gavin, the motion of the oceans and the atmosphere. So, it's kind of lovely because here we get to start at a very lovely and near and dear to our heart part of our solar system. It all starts with the sun. So, Gavin, why do we care so much about the sun when we think about winds and waves?
Yeah, that's a fantastic question, Graham. And I really liked those figures you showed with all of the motion. These are two fluids we're talking about. It's easy to understand the ocean as a fluid because it's water, but also we can understand the atmosphere and the motion of that atmosphere also as a moving fluid. And so fluids normally move when you add energy to a system. So where is the energy coming from the Earth, Graham? It's coming from, as you said, the sun. And so why are things moving? How is the sun interacting with Earth to give it energy?
Yeah. And so that's right. So the when we think about winds and waves and stuff like that, that's all about the Earth trying to move energy around that has been unequally distributed on its surface. And the reason we don't get a perfect, even coating of energy on Earth's surface is because of our round shape of our Earth, right? So we all know that it's warm close to the equator, right? Like California is so much warmer than Alaska, and it's cooler closer to the poles. And that has to do with the way that sunlight hits the Earth. So when sunlight hits the equator, really that whole circle is kind of hitting that area directly. But when you get further up, because the Earth is sloped away, right? It's a sphere and it slopes away, that spreads that sunlight out over more area. So you end up getting less energy at any given point.
Got it, Graham. So this is basically making a gradient between the poles and the equator from low energy to high energy.
Yeah, that's exactly right. And so then if we're going to start understanding how things move around, we need to kind of keep track of what heat and energy means for pressure. And so when we've got hot air, right, those molecules are moving really fast, and that puts a lot of space in between them. So that makes them lower pressure. And when we've got cold air, those molecules are moving slowly. They're a little bit sluggish. They kind of clump together more. And so those are packed in more tightly. And so they're higher pressure. And that starts to matter then when we think about how fluids flow. So, Gavin, what's a fluid?
Well, fluid is basically matter, Graham. It's a collection of matter, in this case, liquids or gases, right?
Yeah, that's right. So it's anything that can flow, anything that can kind of move around. And so when we think about it in terms of these warm, cold molecules and the way they're moving past each other, fluids are always going to flow from a place of high pressure where it's packed in to low pressure. It's always going to want to go from being cramped to kind of stretching out and relaxing the best that it can.
Yeah. So Graham, I'm seeing a theme here. We've got high pressure to low pressure going on in Earth, and we know fluids will flow from high pressure to low pressure. So the big reveal, how is this affecting the motion of the oceans and atmospheres?
Yeah. So on an ideal Earth, or maybe on a simplified Earth, what will happen is our cold areas are then going to, all that cold air is going to flow towards our warm equator. It's going to go from this dense high pressure zone over here to this low pressure zone over here. And so that's going to create a surface flow, which we often think of as a wind. And it's going to set up these cells where as the warm air gets up to the equator, it's going to get pushed up into the air where it cools down and falls back down at the poles. And so this sort of circular movement we call a convection cell.
Ah, convection cell. So we're talking about the atmosphere still here. You mentioned winds. And so you're telling me that wind motion is actually very similar in terms of how it moves, like in a convection cell, to say boiling a pot of water. It goes, when you put heat in it, it's going to convect and move in this cell. Is this right, Graham?
Yeah, that's exactly right. And so these cells are how we can start to set up these sort of these long-term motions of wind through the atmosphere. But it's a little bit more complicated than that because we live on a rotating sphere. So what happens is on our rotating sphere, when we start to move across it as a mass of wind or water, we're going to be affected by that rotation with what's called the Coriolis effect. So if we move in a straight line, going up from the equator or down from the equator, just moving away from the equator, it's actually going to cause us to sort of veer in the direction of Earth's rotation. So we'll start to swing off to the west, to the east. And if we start moving in towards the equator, that's actually going to veer us off to the west in the opposite direction of Earth's rotation. So in terms of our Hadley cells that we were thinking about there, if we're going from the cold poles to the warm equator, as we get to the equator, we should start to swing off to the west a little bit. And so when we kind of put this all together with the winds, that is exactly what happens at the equator, but it gets a little bit more complicated. Gavin, we just went from poles and equators to these, they look like almost sausages wrapped around the Earth.
That's right. So Graham, these basically each one of these cells, right? Because we said it's not moving in a straight line. It's moving as a cell now. The atmospheric motion is moving as a cell. You have three different types of cells. Those are the polar cells, the Ferrel cells, and the Hadley cells. And so basically understanding the fluid motion setup we just talked about and the Coriolis effect is basically all we need to do to understand the three cells of Earth's atmospheric motion. Is that right?
Yeah, that's exactly right. So yeah, we get these sort of local cells that sort of space themselves out between the equator and the North Pole. And we get some familiar wind patterns like the westerlies that we see at the mid latitudes and the easterly trade winds coming out of the east and flowing to the west. But as we often find in nature, it ends up being a little bit more complicated. So this video shows some reconstructions of how wind patterns actually vary throughout a year. And you see that you get these local cells that tend to rotate within themselves. You've got continents and oceans up here. You've got different levels of the atmosphere. It's really a lot of things going on.
Graham, I love looking at models like these because it really reminds me that the atmosphere is a fluid, because this looks just like what happens when I take my hot chocolate and I stir it with my spoon. I get cells that are moving around just like that.
Yeah, I like that analogy. It's a way to sort of like help understand it. It's sometimes hard to think about how the atmosphere moves. It's made of air. It's hard to see, but as long as we remember that it's a fluid, it's just like our water in the way that it's going to kind of whirl and flow around.
Yeah.
So we've got our winds, Gavin. Now what?
Well, Graham, this is a really good segue because to understand ocean movement, it's a good place to start is wind movement. So I'll get to that in a second. But first, let's talk about the two basically parcels of water that make up the ocean. One might say, Gavin, the ocean is just one big bowl of water, but it actually is sort of set up into a column. And in that column, you have the surface oceans, which are warm. They are well mixed because they are interacting with that wind that's moving above them. And the deep oceans are very cold and they're not well mixed. And in between those, you have a thing called the thermocline, which is basically just the thermal barrier between those well mixed, warm surface waters and those not well mixed, deep ocean waters. And the key here is that that we'll start with is that those surface waters are being moved by the winds that we just talked about.
Yeah, that's awesome. And I love how you've got this figure here, Gavin, that shows kind of how quickly these things turn around. The surface ocean is really getting stirred up just in a matter of years or less. Whereas once we start diving into the deep ocean, it's taking like thousands of years, geologic timescales to get that mixing. That's incredible.
Yeah.
Never would have thought that just looking at that big blue ocean. Great. Okay, so yeah, so let's start up at the surface, right? We've got our mind thinking about winds. You mentioned that the surface ocean is driven closely by winds. And so let's think about how our winds drive that major surface ocean circulation. So we talked about those eastward moving trade winds. And so those are going to, westward moving trade winds, easterlies that flow from the east to the west. Wind directions always mix me up, Gavin.
Yeah, it mixes me up as well, Graham.
So what happens is it starts driving our water near the equator off to the west, but that old Coriolis force also affects things moving along latitude lines, and it ends up pushing these water masses out away from the equator, out poleward. So to the north in the northern hemisphere and to the south in the southern hemisphere.
This is kind of neat, Graham. So that when you look at the surface rotations of the surface ocean, they kind of mimic what the atmospheric motions will do, right? Generally.
Yeah, that's exactly right. So if we look here along the equator, right, most things are trying to move off to the west here. And then if we pop up and look up in the mid latitudes where the westerlies dominate, you see most things moving off to the west. Or moving out of the west and off to the east.
Right. So those are following the Hadley cells near the equator and the Ferrel cells near the higher latitudes.
Yeah, that's exactly right. And so with these two different wind motions and a little bit of a sprinkle of Coriolis effect, what we start developing are these gyres. So we get these big sort of rotating masses of water out in the ocean on the surface. But there's one exception to that, Gavin. And where is that exception really notable?
Well, Graham, I think the exception's in the Atlantic. Is that what you were thinking?
Oh, well, I was going to say in the Southern Ocean where we actually get a great big wind tunnel. But I like where your head's at. You're starting to think you're getting ahead to thinking about some of the Atlantic stuff here.
Right. I'm a step ahead of us, but you're right. And that is that Southern Ocean basically has no continents in between it. So instead of moving and crashing into the continents, the winds are just like zooming around the whole Earth.
Yeah, that's exactly right. And so we've got these big ocean gyres going on here. And then through those, interrupting them, you've got, or not interrupting them, but sort of superimposed on them. And I'm just going to speed this up a little bit. You've got all these smaller scale eddies. And so when we actually think about how the ocean's moving, it's more than just those, big major gyres, but there's all this stuff superimposed on top of it as well.
So cool. Look at the Gulf of Mexico. It's just a couple eddies just like constantly spinning around. Really
just
interesting.
Rolling around. And there's this great big major current going up here, which I'm looking forward. I know you're going to be talking about that in just a little bit.
Nice foreshadowing there, Graham.
Yeah. But before we start talking about that big current in the Atlantic, let's bring this a little bit closer to home.
Yeah, Graham. I love when we can like really understand what's going on locally based on these like global scale processes. So we were talking about winds and we were talking about how they affect ocean currents. And a really, really interesting place to see this in effect is Monterey Bay. So if you look here on the left, Monterey Bay's geometry is such that when you pass winds from north to south across the mouth of that bay, it's actually causing these local gyres, one really on the inboard side of the bay, one just outboard of the bay. And what those gyres are doing effectively to the oceans is that they're driving upwelling of deep, cold, and nutrient-dense waters up to the surface of the ocean in the Pacific, right out in Santa Cruz. So, Graham, I love to talk about this quick anecdote about like what this effect has on our daily life, right? So when I moved out to Santa Cruz, I was moving from the Atlantic, and I was doing it in the late summer. And so I'm used to swimming in the Atlantic Ocean, and it's nice and warm in the late summer. It can get almost to 70 degrees. And so got my swim trunks. I'm all ready to jump into the Pacific. And all of a sudden it's like 55 degrees. It's so cold. And the reason it's so cold all the time in the Pacific, and why folks like Jack O'Neill had to invent the wetsuit, is because you're always getting these very cold waters being upwelled to the surface. That also, as I said, those deep waters are very nutrient dense. That also has to do with why Monterey Bay is teeming with life, because it's always got nutrients coming from the surface, and that affects everything from microfauna to megafauna. So that's really how we understand Monterey Bay is a function of these surface currents.
Oh, that's just so cool. And that's such a good point. I remember the first time when I first moved out to Santa Cruz, I was like, ooh, jumping into the Pacific. And oh, it is frigid. Summer, winter, fall, and spring. It doesn't matter what season, you've always got those deep waters coming up to chill you.
That's exactly right, Graham. So, but this is actually a really good segue into the last part of the talk. So ocean circulation, Graham. Take us through this. What is this called, and why do I have something called the conveyor belt here?
Yeah, so this is the ocean. There's many names out here for it. The Great Ocean Conveyor Belt is basically these masses of water that aren't just moving in those gyres and eddies locally, but this is the major sort of directional movement of water masses across the Earth's surface. And they break down into surface waters and deep waters. So this process is bringing conveying waters across the surface into the deep ocean and back around. And who's this chap who we've got on the screen here? He must have had something to do with this notion.
Well, Graham, this is one of my science idols, so I love to talk about him every time I can. His name is Wally Broecker, and he was the father of modern ocean circulation understanding, or basically ocean science in a way. So he was the one who actually came up with this ocean conveyor belt, and him and his contemporaries were the ones who really brought us to our modern understanding of this. So this is, again, Wally Broecker, and he died recently, but before he did, I got to meet him, and he was a really cool guy. So he was really, really responsible for our understanding of this great conveyor belt. So Graham, you'd mentioned that we're moving things around with warm, shallow currents and cold, deep currents. And so there's obviously a temperature gradient to this, or a temperature component to this. But let's jump in. Another word for this conveyor belt is the thermohaline cycle. But before we jump into the actual mechanisms, let's look at this in cross section as well, because it's kind of easier maybe to understand it in cross section. So here we have I put a yellow line across the Atlantic because it's a good place to understand this. So we're now looking at the Atlantic Ocean in cross section. And what's happening on this global scale from hemisphere to hemisphere is that you have cold waters in the poles, which get cold and saline. That's our thermohaline, which we'll talk about in a second. They get cold and dense, in other words, and they sink. And those, basically, you're pushing those water masses down, you're driving them to the other pole, and at the same time, you're pulling warm surface fluids up to the north.
Nice. Yeah. And so, yeah, you can sort of see this process of warm, salty waters coming up from the equator, cooling off, going from warm and salty to cold and salty, sinking down, and then starting to come back up in the south and sink back down in the south. So you can kind of see, right, like everything's moving all over. And you were talking about this thermohaline, right? Yeah. It's not just warmth, it's not just salt, but it's the two of them.
That's right. Yeah. So this jargony word, thermohaline, thermo meaning temperature, haline meaning salinity. So again, we're talking about this as a conveyor belt because you're basically moving water masses based on their density and their temperature. And so we mentioned that really the areas of the Earth that drive this process are the poles. And the reason that this all kind of can start. You can start by thinking of this in the poles, is that the poles are where warm waters go to get cold and saltier. So the reason they get colder is obviously because the poles are colder, and the reason they get saltier is because you form this thing called sea ice at the poles. So really simply, sea ice is the same thing as like a pond freezing over in the winter, except that instead of a pond, it's like all of the Arctic Ocean and a lot of the Southern Ocean freeze over in the winter. And when that freezes over, you basically concentrate the waters beneath it, because when you make ice, you reject salt, and so the water that isn't made into ice gets saltier. And so all of this together drives this sort of schematic that we have here on the right, where you're getting all of your water at your poles sinking, and when that sinks, it moves the whole conveyor belt. Right, Graham?
Nice. Yeah. So that's cool to think about the way that ice starts to play a role in this as well, in terms of like concentrating and driving down some of these salty waters.
Exactly.
That's awesome.
So let's see this in action. Yeah.
I love it. All right. So I'm going to try and speed this up a little bit.
Yeah. So this is a NASA model for what this might look like. Oh, I think you've unspeeded it up, Graham.
I re-slowed it down. My goodness.
Yeah. Okay. So you see those waters kind of coming up. Those surface waters are warm. They're coming up and they're hitting the polar oceans, and then they're getting cold and dense, and they're sinking, and they're being pushed downwards and southwards. Pretty neat, right? And so again, this is we're moving fluids around because we're adding energy to the system. And when we move fluids around, we also move heat around as well, right, Graham?
That's right. Yeah, because these things are going from the equator and to the poles and back again. And so it's a way to not only move that salt around, but also to redistribute that heat across the Earth's surface.
Right. Yeah, and you can see it moving along some of those gyres, and you could see it not running into any continents in the Southern Ocean, so it goes just right around Antarctica. And basically, this is kind of neat because it's connecting all of the Earth's oceans. Interestingly.
Yeah, that's so cool. And so, yeah, so that's cool to think of that as a way to, we think of the Atlantic and the Pacific and the Indian Oceans, but it's all the same water getting moved around over hundreds to thousands of years.
That's right, Graham. That's right. So again, I'd mentioned, sorry to cut you off, but I'm just—
Oh, you're good. You're good.
About these things. I'd mentioned that the ocean currents are moving heat around, so they're affecting weather. And what better a place to look at that than, again, in the Atlantic, where you have the Gulf Stream, right, Graham?
Yeah, so the Gulf Stream is just pumping heat northward, bringing it up from the equator and the Gulf of Mexico, and bringing that heat up into the North Atlantic. And so it does go along the coast of the US a little bit in the south, but then it peels off and goes out into the eastern part of the North Atlantic and brings all this warmth over to Europe. And this is why we have such equitable climates, or such comfortable climates in Europe. So Gavin, take me through what's going on here. Why do I see Big Ben in the background?
Well, Graham, as you said, Europe, especially the British Isles, are the best place to really understand or see the effects of this ocean circulation and the heat that brings, and the effects of that on climate. So if we look at this map here on the top left, the British Isles are at a very similar latitude to northern Canada. So northern Canada in the winters or basically mostly year round, have super low temperatures compared to lower latitudes. But is that the case for the British Isles? Given that they're at the same latitude, we'd expect them to get the same energy from the sun, but are they the same temperatures, Graham?
Yeah, so you put in here a little plot showing the maximum and minimum temperatures, and the lowest, this plot doesn't even get as low as 30 degrees Fahrenheit. And I live in New Hampshire now, which is at the close to the latitude of Spain. And I woke up to 30 degrees this morning. And so I can say it's much colder here.
Right. So this temperature gradient is from London. And you can see that London basically has a similar temperature to like where I grew up in New York, even though it's at the same latitude as northern Canada. So something must be going on here. And it is that ocean circulation effect on temperature. You're bringing those warm Gulf Stream airs up and they're smashing right into the British Isles, Graham.
Yeah, making it nice and balmy. Wonderful. All right. So we've talked about all this, that, and the other thing about how ocean currents move, but who figured this out? How do we know this?
That's right, Graham. So this is a great question. As we showed before, you do have some satellite imagery. So you can map from satellites how heat works in the surface ocean. But the deep ocean, you can't really get that much information like that. So people like Wally Broker, again, and his contemporaries started taking these research cruises. So here's an example of what one of those research vessels would look like. And they just sailed around all of the Earth's oceans. And while they were doing it, they threw out probes like this one right there. Yeah, right in the bottom there. And so as they're sailing, they're probing the ocean for things that are like chemical tracers. So basically they could use the chemistry of the ocean to map how the ocean was moving. And they did so in a grid-like pattern, which is this map we show here on the right. So these are all the places that those folks sailed their research vessels. And Graham, what does the data look like that they get out of this?
Right. So they're not just taking scoops off the surface, right? They're dropping these probes deeply. So once you start piecing these grids together, you're not only looking at how things spread across the surface of the ocean, but also how things are spreading through the depths of the ocean. So if you take a number of measurements along one line, and then you start putting those lines together, we can start building a new view, a new three-dimensional view of the ocean.
Yeah, that's exactly right. And so this is an example of iron, but they have this for a lot of different elements. And basically this is really, really pioneered what we know about ocean, especially deep ocean mixing. So these are really important data and a huge scientific undertaking. This is some triumphant data right here, Graham.
Yeah, this is awesome to sort of see, just to kind of know where iron is found throughout the ocean. And yeah, no, it's cool. And these are exactly the ways that we put together how the currents are moving through the deeps and how water gets redistributed over the Earth's surface. So
exactly, Graham. So cool. This is a really neat topic.
So fun. It made it worth all the seasickness we've had out here.
That's right. So Graham, I think we might have done the motions of the oceans and atmospheres. So what are we going to do next week? I'm honestly kind of done with the ocean. I need to get to dry land.
Thank goodness. I'm so glad you said that. Let's say we get to dry land and enjoy some good old plants. Get back to a little greenery.
That's right, Graham. And I bet you the people in the audience are like, plants? You guys know about rocks, not plants. But it turns out that the history of plants and the history of geology are somewhat intertwined. So we'll kind of pull that all together, and we'll think about plants and climate and geology and how they're changing at the same time and affecting each other. So it should be a fun one next month.
I'm looking forward to it.
What do you think, Marisa?
That sounds great. Yeah, we're kind of branching out from our typical geology topics with these past few ones. You don't really think of rocks as the first thing that comes to mind when you talk about, the weather and the ocean, but clearly it's all connected. That was really fascinating. And yeah, good reminder that the ocean is not always cold all over the world, just here.
Exactly right.
Unfortunately. But great. I'm very excited to learn about plants through the lens of geology next month. That sounds awesome. And also a reminder that we do allow people to submit photos for identification by the Geology Gents. And we have a series of photos that came in from a family in the Santa Cruz Mountains, Sonia and her daughter Alessandra, and they are active participants in museum programs and really love science. And they have been stumped by some rocks that they've been finding up in the Felton area. And Alessandra, who I think is around 7, has been finding so many cool fossils. It's really amazing. And they are curious about what formation the fossils that they are finding are from. So I'm going to share some pictures from Alessandra and Sonia for Gavin and Graham to look at. So you can see, speaking of plants, it looks like we've got a fossil leaf here, as well as some shell, maybe imprints.
Beautiful.
That's Alessandra.
So neat.
She's got her tools of the trade.
Wow, look, yeah. First off,
what are you guys seeing here?
Yeah. First off, I just want to say thank you to Sonia and Alessandra for sharing these really cool pictures. And we're so happy that you're excited about the rocks in your area. This is like really neat stuff. And it's a really good way of learning about the history, especially the geologic history of where you're living at. So good on you guys. Nice job.
Yeah, these are some awesome fossils you've picked up, and it's always fun to see the work of a fellow geoscientist, to see the rocks that you've been cracking open and digging up. So yeah, this is exceptional.
Yeah, and it looks, we'll get to the science in a second, but it does look like Alessandra has a future in fossil preservation. Really nice work. This is good. So Graham, I like to start off with a very holistic picture. Like we're seeing they're in the Santa Cruz Mountains, right? That's at least several miles off the modern ocean. And they're seeing sandstones and they're seeing shells. So what does that tell us about what that place was like, what that environment was like up in Felton millions of years ago?
Yeah, the great place to start. That's right. We're seeing marine rocks in a place that is now hundreds of feet above modern sea level. And that tells us, that clues us back into the history of the geologic history of California, that the coast of California, especially right here in Santa Cruz and in the Santa Cruz Mountains, is getting lifted up. And these million-year-old, millions to tens of millions-year-old marine deposits are getting hoisted up above sea level and brought up into the mountains by those tectonic forces.
That's right, Graham. So I always like to think about myself if I had a time machine. So Alessandra, if you jumped into a time machine and you just stayed at home, but you're in your time machine and you went back 10 million years, you'd be swimming in the ocean. So that's where these sorts of samples are forming. So I know that you all asked about the formations. And so Marisa and Graham and I had the opportunity to talk about this a little bit before we got on here and to talk about what your rocks are. And so in the Santa Cruz Mountains, we would often think of a few different formations. Yes, look at this geologic map. Very interesting. Yeah. So I'm not, you could see that based on the colors here, you have very different rock formations in these areas. I usually think of the Santa Margarita sandstone as around this area. And Marisa, you said that the Monterey formation is probably what they're looking at as well, right?
Yeah, it did. So that's the thing. You think of what you find up in the mountains, and there's lots of different outcroppings depending on where you are in the mountains. And right up in here, where the San Lorenzo Valley is, it's very varied. So it's not so simple, which is why I had talked to Alessandra about this before. And I really, just from hearing her story, I wasn't able to tell her, but they sent along their address. And that's how I was able to figure out that they are kind of within this area, which is the Monterey Formation. And this is a map that we have on the museum's website. We have got a guide to the rocks of Santa Cruz County. So you can look at this map in more detail there. And then look at the different types of rocks that we have too. But also when I'm looking at this, the Santa Margarita formation, I think of as like a lot chunkier. And I know that we often find like shark teeth and sand dollars, but not so much with the bivalves, I feel too. So that's like another clue for me. But the way the color and like the texture here also seems a little bit more like the Monterey formation also. Would you guys agree?
Yeah, the Santa Margarita, it's really sugary, is the way I kind of
Mhm.
think about it, right? It's like big chunky sugar or salt, these big, kind of sharp quartz crystals. They aren't held together super well. This is definitely a little bit kind of muddier. There's a little bit more mud and muck that's helping to hold this together rather than that, really grainy, sugary Santa Margarita.
Yeah. And I mean, they're close to the Santa Margarita too. So it might be that if you're going on a longer hike, maybe you're finding some different kinds of fossils too. Because it is like we were talking about, so varied. And this is more like 15 million years or so, right? And then the Santa Margarita is 10 to 12 million years. So even within just like walking a mile or so in a different direction, you could be looking at things from millions of years apart, which is so cool.
How about time travel?
That's right.
Yeah. So great. Well, I hope that helped Alessandra and Sonia. And thanks so much for sharing all those pictures. They also shared some wonderful science videos that Alessandra makes, which is so great.
Awesome.
Very impressed by Alessandra. So thanks, Gavin and Graham, for helping to identify those and share some of your tips for how to go about starting that process. And I want to also thank Gavin for showing up last weekend for the Museum of the Macabre Halloween event. We talked about dangerous minerals, which is also the subject of the October pop-up. So if you weren't able to watch that, you can go back and watch that. That previous installment, and can't wait to talk about plants next month. So exciting.
Looking forward to it. Should be fun.
Great. Well, thanks guys, and see you next time.